Hey everyone, welcome back to the Daily Dose of Space. Today, we're diving into one of the wildest ideas to come out of modern astronomy. An idea that sounds almost like science fiction, but is now being seriously considered because of new JWST observations. What if the very first stars in the universe weren't stars the way we think of them at all? What if they were enormous, slow-burning objects powered not by nuclear fusion, but by dark matter itself? This is the dark star hypothesis. And right now, a new study is bringing it back into the spotlight, not as a fringe theory, but as something that might actually explain a few of JWST's weirdest observations. So, let's break down what a dark star really is, why JWST may be hinting at them, and what this would mean for the early universe. Dark matter makes up about 85% of all matter in the universe. We know it's there because of gravity. Galaxies rotate too fast to stay together without it, but we've never seen it directly. And one of the big possibilities is that dark matter particles could sometimes annihilate each other and release energy. Normally, that energy doesn't matter much. But in the early universe, things were different. The first stars formed inside massive clouds of hydrogen and dark matter. And if the dark matter density was high enough, those annihilations could act like a kind of slow, steady heating mechanism. Almost like a cosmic warm blanket. That heat would counteract gravity just enough to stop the collapsing cloud from reaching the temperature where fusion begins. No fusion, no standard star, just a giant, puffy, glowing object powered by dark matter instead. And the size? Not small. We're talking 10,000 times the size of the sun, with masses up to 1 million suns, shining dimly in visible light, but extremely bright in the infrared. Exactly the kind of object that JWST is designed to detect. So here's the big question. Did JWST accidentally see something that matches a dark star? When JWST turned its infrared eyes to the early universe, it found something unexpected. Surprisingly bright, surprisingly massive galaxies appearing far earlier than they should. Some of these galaxies, only a few 100 million years after the Big Bang, seem too bright and too large based on our models. Almost like there's a light source inside them that shouldn't be there. A recent study suggested that at least a few of these ultra-bright objects might not be galaxies at all, but rather supermassive dark stars, glowing intensely in the infrared because of their gigantic size and low temperature. To be clear, we're not saying JWST has proven dark stars exist, but the data shows objects with extremely red infrared colors, very high apparent brightness, and sizes too large to be normal early stars. And those three things together line up surprisingly well with the predictions for dark stars. This is why the hypothesis is heating up again. So, what would it mean if dark stars were real? First, it would solve a major tension in cosmology, the JWST early galaxy problem, also known as the too big, too early issue. If dark stars existed, they could mimic bright galaxies, making the early universe appear more evolved than it really was. Second, it could help explain how supermassive black holes formed so fast. A massive dark star collapsing would leave behind a black hole seed thousands of times larger than a typical dead star, giving black holes a head start. And third, and maybe the coolest part, it would be the first actual astrophysical evidence of dark matter doing something other than just gravitating. It would be dark matter interacting, heating, and shaping the first structures in the universe. Basically, dark stars could be the missing link between particle physics and early cosmic evolution. But let's slow down for a moment. Every big idea needs to survive a few reality checks. There are other explanations for JWST's bright early objects. For example, extremely massive early star clusters, unusually efficient star formation, or even exotic black hole accretion. So far, none of these fully solve the problem, but they're not ruled out either. And that's why astronomers are cautious. Dark stars are exciting, but extraordinary claims need extraordinary evidence. The ultimate test will be JWST's spectroscopy. If these objects show the smooth blackbody-like spectra predicted for dark stars, and not the sharp signatures we see in galaxies or star clusters, then things get very interesting. Right now, the data is still coming in. We're basically watching a scientific mystery unfold in real time,